All right, so we're about to start our study of modern physics. We're going to screencast a few concepts here together. We've talked about the fact that light isn't really a wave, although it has all of these wave properties. The reason it isn't really a wave is that it's got particle properties as well. For instance, it travels through a vacuum and has momentum, and it's made up of little bits of energy called photons. So what are the properties of photons? Well, first of all, there are wave properties for photons. And, photons have wavelength. And they have a frequency, and they obey the wave equation. Lambda times frequency equals speed. The speed is obviously the speed of light, c. Now, in terms of the particle properties, there's a couple of them. The first says that photons actually have momentum, and the amount of momentum that they have is proportional to their energy. So there's the momentum equation. Then the other one says that there's a proportionality between the energy of the photon and its frequency. So this is the energy actually of a little bit of a quantum of a photon of light, quantum of light called a photon, and the energy of that little bit is proportional to the frequency. It's also proportional to h, which is Planck's constant. Now, how much is Planck's constant? Well, it's 6.63 times 10 to the minus 34 joule seconds, so it's very small. So, for instance, let's find the wavelength, energy, and momentum of photons if we're listening to an AM 690 kilohertz. AM 690 is 690 kilohertz. So that's, of course, telling us the frequency. So we know the frequency is 690 kilohertz. Kilo is 10 to the 3, so this is 6.9 times 10 to the 5 hertz. Now we want to find the wavelength, the energy, and the momentum. Well, lambda f is c, so lambda just equals c over f. C is the speed of light, 3 times 10 to the 8th meters per second. We divide by 6.9 times 10 to the 5 hertz, and that'll tell us the wavelength. Let's get our calculator ready here. So, where are we? Okay, so 3 times 10 to the 8 divided by 6.9 times 10 to the 5. So 435 meters basically is the wavelength. That's an extremely long wavelength, 435 meters. The energy, well, that's Planck's constant times the frequency, so that's 6.63 times 10 to the minus 34 joule seconds. And then a hertz is actually a reciprocal second. So the second and reciprocal second cancels out. And let's see how much this energy is. Now, it's going to be already small, but this is the energy of a single quantum, right? So not surprising that it'd be fairly small. So there's Planck's constant. Then we multiply by 6.9 times 10 to the 5, which is the frequency. Let's try that again. 6.63 E34, change sign, enter, tau yen. Okay, let's just get it. Okay, so yes, the calculator is not cooperating. It's a cheap desktop model, so it's 4.57 times 10 to the minus 28 joules for a single photon. And a single photon will also have momentum, and that momentum will just be its energy divided by the speed of light constant. So we got 4.757 times 10 to the minus 28 divided by 3 times 10 to the 8. So that's going to be 0.52 times 10 to the minus 36, and momentum units are kilogram meters per second. So let's try dropping that in here. There we go. So that is a fairly straightforward example. So Planck's constant, really small number, 6.63 times 10 to the minus 34 joule seconds. It can also be written in another set of units. When we deal with atomic physics and with quantum mechanics, there's a more convenient energy unit to use, and this is the electron volt. The electron volt, EV, relies on us knowing what the fundamental charge is. You may recall that E is 1.6 times 10 to the minus 19 coulombs. That's the charge on an electron or on a proton. And then a volt is, of course, a joule per coulomb. So this is an E and this is a V, electron volt. Well, you can see, because the coulombs cancel, that it's an energy unit. And an electron volt equals 1.6 times 10 to the minus 19 joules. So we can do a conversion here for converting Planck's constant from electron volts into joules. We're just going to multiply by 1 EV is 1.6 times, what's happening there? 1.6 times 10 to the minus 19 joules. Sorry about this mess here. That's just supposed to be multiplication there. And then if you work that out, you get 4.14 times 10 to the minus 15. This joule cancels out this joule. The second remains, and the EV remains. So you get electron volt seconds. So, yeah, this is pretty big. But it's meant to be up on this line, so you're multiplying this version of Planck's constant by this conversion factor. And that gives you the value of Planck's constant in electron volt units. Now we can use that, for instance. Let's imagine we had a photon that's got an energy of 2.5 EVs. EVs, electron volts, is a unit of energy. So we know what the energy is then. It's 2.5 electron volts, 2.5 EVs, and we're asked for its wavelength and its momentum. Well, we know two things, that the energy is proportional to the frequency, and we know our wave equation, lambda f equals c. So if we want the wavelength, we can see it's going to be c over f, but we can see that reciprocal f is going to be h over e. So we can write this as hc over e. So for our calculation then, we're going to substitute in Planck's constant, 4.14 times 10 to the minus 15 EV seconds. And then the speed of light constant, and then we're going to divide by the energy. Well, because we know the energy is 2.5 electron volts, we see that the electron volts is going to cancel out. C, just 3 times 10 to the 8th meters per second. You see now the seconds will cancel out, and you're left with meters. So this is a good unit for wavelength, or be a good number for wavelength. So this calculator doesn't seem to want to do powers of 10 here, so maybe I'll have to do them myself. But let's just see what the magnitude is. So it looks like 4.9, basically 5.0. And let's see, it looks like that's going to be times 10 to the minus 7 meters, which is 500 nanometers. So that's the wavelength of that photon. And we're also asked for its Send that over. There we go. That is not exactly where I wanted it. There's my cursor. There we go. Let's drag it down and drop it right there. Didn't like that. Come on, you. Move. Right here. Okay, I give up. Try cutting it. And then here, paste it. All right. Boy, that's frustrating. Okay, and then for the momentum, well, the momentum, the energy is proportional to the momentum, so the momentum is just the speed of light constant over the energy. Now, oh, sorry, E over C. And momentum units would usually be given in terms of kilogram meters per second, but the atomic unit is actually electron volts over C. So you just leave C. You don't put in the 3 times 10 to the 8. You just leave that as a constant there. And so momentum units are written in this way. So that just makes the numbers easier to work with, that's all. Okay. We are dealing with the electromagnetic spectrum, and here it is right here. Here are the wavelengths for visible light, and then the infrared, and then here ultraviolet, and so on for the rest of the spectrum. So you can have a look at that. Mainly we'll probably be talking about the visible spectrum, and you should know probably what the limits are, that it goes from roughly 390 nanometers up to 720 nanometers. You don't really need to know what the divisions are in there, but you should have some sort of idea of the range of wavelengths for visible light. Okay, some simple exercises here related to those equations. Really, there are just 3. There's the wave equation, and then the 2 particle equations for photons. And the next thing we're going to talk about, and we'll pick this up in class, will be how quantum theory applied to electrons. And we'll learn about the de Broglie wavelength.